kinetic art design system with rigid body simulation. Kinetic art, such as mobile sculptures and balance toys, is art that involves movement. The motion is produced by wind, water flow, or an observer. A lot of works have been created by many artists since the early 20th century. Movable objects attract people, but designing shapes which move as a designer intends is not easy. In order to do so, one needs to predict the results considering physics with many trials and errors. Unfortunately, current CAD and CAE tools are insufficient for the design of such dynamic objects because these systems are usually entirely separated. So if the simulation results are not satisfactory, we have to return to the CAD system and try again. In our system, we combined a 3D modeling application with a rigid body simulation engine for aiding the design process of kinetic objects. The system continuously computes the motion of the objects, and the results are visualized as static annotations, such as colored arrows, on the modeling window during the user's modeling operation. Our contributions are summarized as follows. We propose a new 3D CAD system with physical simulation. We introduce an implementation technique to provide real-time response to users' actions and to visualize the motions of the objects, and we developed an application for our system. First, let us show you a movie demonstrating our system. Our system has a modeling interface and rigid body simulator. First, users create shapes such as spheres, cubes, flat boards, and triangle meshes. Second, users connect the shapes with strings. They can change shape properties to dynamic, and a simulator will analyze these motions. Users adjust the string positions and observe the simulation results. Next, we introduce an implementation technique to provide real-time responses to the user's operations. To realize a responsive physical simulation, our system changes the size of the time steps automatically according to the user's operation. When a user is changing the position of an object, quick response is more important than the accuracy of the simulation. Thus, the time step is doubled during the user's drag operation. On the other hand, when a user stops manipulating an object, the simulation should provide a more accurate result. Thus, the time step is reduced by half. Next, we'll talk about the method for visualizing the motions of the objects. If the object is drawn at all the positions the simulator computes, sometimes it is hard to understand the object's motion. To deal with this, our system draws the objects only at the positions where the direction of motion changes. If the center almost stands still, the object is considered as rotating and two magenta arrows are displayed. If the two loci are almost the same, the object is considered as moving without rotation and a blue arrow is displayed. Next, we'll discuss the user studies and results. In the user study, participants were asked to find an appropriate initial position of a sphere so that, when dropped, the sphere would touch all three cubes during its fall. On the left is a non-interactive simulation, so the results cannot be displayed while the sphere is being manipulated. On the right is our system, in which users can adjust the starting position while observing the simulation results. With our system, the testers can find the position in about half the time. This is the other result designed with our system. It is used to find the starting position, which will lead to the sphere ending in the cup. This mobile was also designed with our system. On the left is our design, and the right is a physical model made with 5mm acrylic resin board. This is another example. This mobile is difficult to design without our system due to its three-dimensional configuration. However, with our system, it can be designed more easily. Thank you for your attention.